Welcome everybody. So to this link seminar session, my name is Pierre Popineau, so third-ish year PhD student under the supervision of François Bachelli. And today I'm going to present the result that we obtained with the Schneer from Heriot-Watt University. So the title of this talk is a bit long, but it's about finding a necessary and sufficient condition for stability of a given queuing network with state-dependent departure rates. If I can, yeah, okay. So as an introduction, so as most of you know, reaching a stability condition for a queuing network is something that is, I wouldn't say necessarily easy, but relatively straightforward because there have been many methods that have been developed over the years to obtain such conditions. So we get a variety of tools that exist. So you can think about drift arguments, the famous Forster-Lyapunov theorem, and another set of tools that is very useful to obtain a stability condition for a queuing network is fluid limits, which we're going to tackle in this talk. But sometimes it can be a bit tricky. And on the other hand, instability condition is something that is much harder to obtain because most of the results obtaining stability for queuing networks don't have direct reciprocals. Usually you need to weaken and to relax the conditions that you have initially. Sometimes, and most of the time actually, the instability conditions that you get are loose and you cannot really get clear definition, stability, instability in a general case. So the question that we are going to try and answer in this talk is, given the right assumptions, how can we reach a tight stability condition for a certain family of queuing systems with state-dependent departure rates? So for the outline of this talk, so I'm going just to go through the original motivation for the talk that we had. I'm going to make some quick reminders about fluid limits and the main results linking stability and instability of queuing systems with fluid limits. Then we're going to study a bit more the fluid model for the dynamics that we're considering here, finding a stability condition, then going for the instability condition, and in the last part of this talk, I'm going to talk about a refinement of the stability condition that we managed to have, adding another assumption for the dynamics that we are studying. So this talk is going to be based on the results of two papers. So the first original paper that launched this discussion is a paper from Schneer and Alexander Stoliar that has been published in Queuing Systems in 2020. And the second paper, which is the reciprocal, so giving an instability condition for our queuing system. So it's been posted on arXiv 2 weeks ago, so it's available if you want to read it and to have a more in-depth look at the proofs that we're using here. So the original motivation for this paper was the study of a network with single hop decentralized medium access algorithm. So it's relatively simple. So we consider an undirected graph. So with a set of vertices V, a set of edges E with big N nodes, and we're going to denote by Ni the neighborhood of a given node. So on each node, we're going to place a node I and a Q, and we're going to denote as X the queue length process. So we assume that we have an infinite buffer size. So we're not limited. So you do not have any waiting time before being able to transmit. So we assume that time is slotted, and at the beginning of each time slot, you get a random number of messages that arrive on node I, with this random number of messages that are IID. They do not depend on the time and have a mean lambda I that is strictly positive. So now for the medium access algorithm, so at the beginning of each time slot, each message on the system is going to receive a priority. So this priority is going to be sampled uniformly at random, independently from all the network parameters. And the message with the highest priority in its neighborhood is going to initiate transmission in the network. So now, when you are studying such a network, we can easily compute the probability that a transmission happens in node I, and it's going to be equal to the queue length of node I divided by the. So this is going to be the probability that transmission happens in node I, and we're also going to use a convention that this probability is equal to 0 if there's missing an xj here. So we just, if the denominator is equal to 0, we assume that the probability is equal to 0. So it's going to prevent the degenerate case where you get to know that it's transmitting with no neighbors. So here we can get easily a stochastic recurrence for this QNX process. So which is just simply to say that the number of messages in Qi in time slot k plus 1, just the number of messages that you get at time slot k plus the number of messages that arrived minus the number of messages that left. And this random variable eta I can take values 0 or 1 with this probability that actually you have a transmission knowing the state of the system that is equal to this probability of transmission. And so the initial motivation was to find a condition on the values of lambda I, so the mean number of messages arriving at each node, such that the system is stochastically stable. So now I'm just going to take a small detour by going back to fluid limits. So it's one of the main things that I've studied during my PhD. So just a quick reminder. So we take X, a Markov chain, and two sequences of positive numbers, AN, BN, such that, so there are both increasing sequences of number that go to infinity. And the second condition that we want is the limit of BN over AN that is finite. So here we're going to denote it as XO. And we can define something which we call the fluid scale sequence, which, so Xn of t is 1 over AN times X at time AN times t. And the initial condition is going to be Bn divided by the scaling factor AN.
I have a question.
Yes.
So this is continuous random variable.
Yes. So here I wrote it, sorry, for continuous random variables, but it can also work for slotted and discrete time processes.
But your model is discrete.
So yeah, our model is discrete, but it works as well. So here I wrote it in the general case for continuous time Markov chains, but fluid limits work as well for discrete processes. And so the main idea behind a fluid limit is instead of studying only the queuing process of the one jump, we're going to look at it over AN jumps. And we're going to take the average, so AN jumps, and we divide it by the factor AN. And to complete the study, we're also going to take an initial condition that is also going to grow very large. So here I wrote a general fluid scaling, but usually what we use is AN is equal to N, so which is one of the most simple cases. And we take Bn that is also proportional to N, so that we get this limit that is always finite. And so we're going to call a fluid limit for the Markov chain X, the limiting process. So if we take the limit as N goes to infinity of this fluid scale, the fluid scaled sequence. So these fluid limits have been introduced by Rico and Stoliar to study some queuing properties, but the main link between the fluid limits and stability, it's a theorem from Jim Dye, published in 1995. So we say that the fluid model is stable if and only if this fluid limit X bar reaches 0 whenever the initial condition is of volume 1. And the consequence, if for a given queuing discipline, the fluid model is stable, then the associated Markov chain is positive recurrent, and then we get all the nice properties that we want, the existence of a stationary distribution, and so on. So this condition actually is quite strong. So we want the fluid limits to reach 0 in finite time. So in most cases, so in a lot of cases, actually, it's relatively easy to prove, especially when the fluid model consists in simple ODEs, but some configurations can prove to be harder to study. And so this is what we're going to see here. Now for instability, we would like to get a direct reciprocal for the previous results, but it does not happen. So there is notably one example that has been introduced by Bramson. It gives an example of a stable fluid model with unstable dynamics. So like I said, we need to relax the condition. And so we're going to introduce another definition, which is called weak instability. And so the weak instability states that if we take a fluid limit starting from 0, at any given time, if we leave 0. So if the initial condition, the fluid limit, is empty at time 0, then there exists a finite time delta such that the fluid limit leaves 0. And whenever we leave 0 in the fluid model, we are sure that the fluid process, the associated Markov chain is unstable with a population that is going almost surely to infinity. So, and linking this to our initial problematic is usually, so this result actually gives another condition on the fluid dynamics, is we need to have the fluid dynamics to be defined when for an empty initial condition, which is, like we're going to see, not the case for the model that we're going to study here. And the other thing is, so this is not a direct reciprocal to the previous results, and we're also going to see that sometimes it can give pretty loose instability condition for the system. So now, if we go back to the initial example, so I'm not going to prove it, but we can prove that the queuing system has a fluid model. And so the fluid model here is in the form of a differential equation. So the derivative of the fluid limit depends on the state of the fluid limit, and we get something of the form lambda I minus psi of x of xt. And so if you want to obtain the condition, we are going to use the Jim Dice problem. So I'm just going to take the sum of all these equations. I'm going to bound it from above, saying that here we're summing over just the neighborhood of one node, and so it's going to be lower than if we sum over all the nodes in the system. And in the end, we're going to be able to bound this from above by the sum of lambda I minus 1. So now we can integrate. We assume that the system is empty at time 0, and what we get is a relatively simple stability condition, the sum of lambda I that is strictly less than 1. Now, if we assume, for example, that all the lambda I are equal to the same value lambda, so we're going to get the same arrival stream of jobs for all nodes in the system, we get immediately a stability condition that is lambda lower than 1 over the number of nodes in the system. But we have a problem is as V grows larger, we know that we can see that lambda C goes to 0. So in the case of an infinite graph, the system is never stable. And we know actually that this system is stable. It can be stable even if the graph is infinite. So the question that is arising now is how can we get a tighter stability condition for these dynamics?
I have a question.
Yes,
here.
go on.
Oh, so the sum of lambda I is smaller than 1. I think the right-hand side is a relative coefficient because you specify the rate of departure is related to the Q list of other nodes.
Yeah.
And this is a relative relationship, but the arrival rate, this lambda I, is an absolute rate.
Yeah.
So if there is some confusion here, you're comparing an absolute value arrival rate to a relative value 1.
So actually, this is just like I said, this is just bounds. Just straightforward wanted to use this result from Jim Dice. So we say that we take an initial condition of volume 1, and we want to reach. So yeah, I just figured out that there might be a problem in the calculation, but it does not really matter. What we want is to reach 0 starting from an initial condition of volume 1. And so when you are looking at this kind of dynamics where the departure rate depends on the state of the system at a given moment, this is, like you said, a local condition. So we want to look at the neighborhood of a given node. And the problem is if we do not have more information about the configuration of the graph, like we may have or not, the best way is just to bound from above. And this bound from above actually is quite loose, but lacking more information on the topology of the system, this is the best that you can do if we take a general graph. And so this is why actually you get something that is global. So the rival on one node, and here actually you have a one because I decided to bound it globally over the whole graph. Yes.
Maybe it is related to the question of
Yeah.
The lambda I, are they normalized to something?
No, not necessarily, no.
For me, there are some units in lambda. One, there is no limit, so there's a problem of.
Yeah, yes. Yeah, I see. I see. So yeah, you can take.
Yeah, that's fine.
Yeah, so this is so actually you have a unit, but actually it has no dimension. It's just the number of messages that arrive at each time slot in the system. So because it is a time slot, then it does not necessarily have a unit. It's just arbitrary.
I understand. It's a kind of normalization.
Yeah. Yes. But this is actually so you. If you study queuing systems, so
and I agree. If you sum all the probability of arrival in one this point,
yeah,
it must not be more than one.
Yes.
So
yeah. So now we can move to the question of having a tighter stability condition for such dynamics. So we're going to define a set D. So this is going to be the set of vectors. So I'm going to denote these coordinates as nu I, such that for all coordinates, nu I is lower than psi I of a certain vector. There's a mismatch in notation. So this is a phi. So this is the set of configurations. So this is the set of vectors for which there is a configuration of the networks that has a higher coordinate-wise departure rate than the vector nu that we are looking at. So if you look at the orthent, so R plus N, for each Q, you're going to get a maximum departure rate. And so this is going to define a fixed region of the positive orthent R plus N. And so we are going to look at all the vectors nu that are inside this closed volume of the positive orthent. And so the stability condition that has been proven by Sevachner and Alexander Stoliar is if our rival vectors lambda I are smaller than a vector nu I in this set D, then the queuing system is stable. And so actually this gives a relaxed condition, which is actually proves to be sorry, not a relaxed, but a stronger condition for stability. And it proves, so this is what they conjectured in the paper, that it is actually tight for the dynamics that they were studying. But it is also interesting to see that actually, before we get some kind of very strong absolute condition on the globality of the graph, here we get a case-by-case, quote unquote, condition for stability. Now we only need the rival rate to be lower than one possible configuration, not the configuration that we are looking at, but one possible configuration. If there exists a configuration that allows the system to be empty in finite time, then the system is stable. And so this theorem actually is based on this lemma. So it's quite long, but we need the fluid model to get 4 conditions. So the first condition is just the equation during the fluid model. So this is already verified in our case. So the second condition. So the second conditions, I can rephrase it a bit simpler, saying that you cannot have one Q, so one coordinate of the fluid model that is emptied alone. If one is empty, then all must be empty. So this you cannot. So if you look still at the positive orthent, you cannot have one coordinate that goes to 0 independently. If one coordinate is going to 0, all the other coordinates in the fluid model have to go to 0 at the same moment. And so we need as well 2 more conditions. So these conditions are going to be linked for the fluid departure rate, so psi. So we need these functions to be non-increasing in their coordinates. So psi I is non-increasing in xj for j different than I. And the last thing is we need these functions to be 0 homogeneous. In a sense that psi of Sx is equal to psi I of x for all S strictly positive and for all x. And so now, if we get these four assumptions, we can find two constants, k and delta, and a time t, such that whenever we start with a volume k in the fluid model, at time t, we're going to go below delta for the volume of the fluid model. So this is, so actually this is not directly linked to fluid models. So this is a more general lemma that works for all Lipschitz trajectories for which you get these four assumptions. But in our case, we're going to use it to obtain stability in the queuing system. So I'm just sorry for the I forgot to. So people that have been working with LaTeX know why this can happen. I'm just going to give a quick overlook of the proof because I think it was a neat trick that they managed to find. So we're going to take a vector nu inside our set D that is defined right here. So by definition, we can find a vector t such that coordinate-wise you get nu I that is lower than psi I of t. And so we're going to take the function big F that is going to be the maximum of yi divided by these coordinates ti. And we're just going to denote as bk the index or indices for which this maximum is reached. So if we take the derivative of this function f applied to our fluid system x bar, so we're going to get immediately the differential equation that we had earlier. And now, because k is taken inside this R maximum, we know that x bar k divided by tk, sorry, there's a typo here, is going to be greater than xj divided by tj for all j. So now we're going to invert this, and property 3 states that the function psi k is going to be non-increasing in all coordinates different than k. So we're just going to write it. And so now in all the coordinates inside this function psi k, you can find this factor x bar k divided by tk that appears in all coordinates. And so we can simply use the zero homogeneity of our function to say that psi k of x bar is going to be greater always than psi k of t, and so greater than our vector nu k. And so now to conclude the proof, just say, so I'm just going to rewrite f prime of x. I'm going to add this nu k, so I just use the minus nu k plus nu k inside the parentheses. And we know that this part on the right is going to be strictly negative from the previous results. And here, because we took lambda k, lambda, such that we have lambda I that is lower than nu I, this part is also strictly negative. And so we can find that the function f prime is negative and bounded away from 0 as long as f is positive, and bounded away from 0. And so we get a strictly decreasing function. And so we know that if we start from a given initial condition, we're going to drop below actually any value delta that we want. And so now, if we want to conclude and to obtain stability for the fluid model, sorry, and then the Markov chain, we're just going to apply this lemma with k is equal to 1, so starting with volume 1, and the value delta that is 1 minus epsilon for a given epsilon strictly positive. And so we can use, so this is one of the many lemmas that were introduced in Jim Dye's paper that are linking the stability of the fluid model with the stability of the Markov chain. And so this gives us a positive recurrence for the Markov chain. And so now, in the original system and in the example that we are looking into, the rate psi satisfies the assumptions 1 to 4 that we mentioned in this lemma. And so as such, we can obtain that the system actually is stable for all the arrival wells that are inside the set D that we defined earlier. So now there's also another notation that you can use. So instead of taking streams, so lambda I for each server, you can see it as one big stream of jobs of messages that is arriving in the system, and then all the messages are going to be independently routed with probability pi to qi. So this is just a change to introduce another notation. And so we can rewrite the set D. So I'm going to change the notation. So I'm calling it D prime because now we're having an interval of real numbers. And so this set of D prime is just going to be the set of real numbers nu, such that nu is lower than 1 over pi times psi I of p. And so the stability condition becomes that the system is stable if lambda is strictly lower than lambda star, where lambda star is the supremum of this real interval. And in terms of notation, lambda star is the maximum of the smallest coordinate of the vector 1 over pi times psi I of x. So this is just another notation for this for the same result that can be useful if you're working with one flow of messages arriving in the system and then it's going to be routed to different to all the different queues. So now, if we go back to the example, so now still the same setup, but if we take an n-1 regular graph, so meaning that each node in the graph has the same degree n-1, we can take a vector y that is inside our set D, and we assume that the system is stable. So lambda is strictly less than psi I of y for all coordinates. Then by definition, we're just going to rewrite what psi I of y is. We can sum the n inequalities. And so now we're just going to use a small trick. So here we have something that is of the form x plus 1 over x. By definition, x plus 1 over x is always greater than 2. So everything in the end simplifies, and we are left with m times n. And so the stability condition simplifies to become lambda that is strictly lower than 1 over m. And in particular, if we take n nodes in a circle, so with m is equal to, so n-1 is equal to 2, so each node has 2 neighbors, then we get lambda that is lower than 1/3, which is the stability condition for decentralized medium access algorithm for nodes in a circle. And so what's interesting is compared to the previous stability condition where I just used straightforward the Jim-Dice theorem, now we get something that does not depend on the graph size. So this still holds if the graph is infinite. So now, once we have this, comes the question of instability. So is there an arrival rate lambda greater than lambda star such that the system is stable? So we cannot use the reciprocal that I presented in the introduction because here the dynamics are not defined when x is equal to 0. Actually, you can prove that you can get, so the value is just not defined here. And this is the case for most of the zero homogeneous function. You're not defined towards 0 because you can find as many different values for the value of the function in 0. So we cannot use directly the free limit theorems about instability. So what we're going to do is, because we cannot prove instability in the free domain, we're just going to revert back to the original Markov chain and hopefully find interesting properties. And talking about interesting properties, we're going to talk about stochastic domination. So stochastic domination is just a way to define a partial order on random variables and stochastic processes. We say that x dominates y if the probability that x is greater than y is equal to 1. So if x is greater than 1, P almost surely. And so we're going to use this here. And so the result that we have is if we take two realizations of our original dynamics, so we're going to take arrival rates lambda x, lambda y, initial conditions x0, y0, departure rates psi I, phi I. Then we get 3 sufficient conditions for the process x, the queuing process x, to dominate the queuing process y. So first, if the initial condition in x is greater than the initial condition in y, we are sure to have almost surely more points in x than in y. Second condition, if more messages arrive in x than messages arrive in y, then you are sure to get more messages in X than in Y. And the last thing is if the departure rates in X are lower than the departure rates in Y, meaning that more messages are transmitted in Y than messages are transmitted in X, we're also ensured to get a more crowded system in X than in Y. And so we're mostly going to use assumption C here, even though A and B are also interesting in their own rights. But another way to translate condition C is if you make life worse for one person in the system, then it's going to make the life worse for everybody in the system. If we slow the rate of transmission for one queue, one user in the system, then it's going to make the system more crowded in all configurations. And so now we're going to use this stochastic domination in order to prove instability in our case. So now we're going to take a value lambda that is not, for which the system is not stable. So, and the goal is to prove actually that if we take a value of lambda for which, outside the set D prime that we defined earlier, then the system is unstable. So what we're going to do is we're going also to take a value Z, and the value Z is not going to be taken at random. It's going to be a maximizer of this function, so the minimum coordinate of the vector 1 over pj time psi j of y. So this is going to be a maximizer of the rates of transmission in the system and a maximizer of the smallest rate of transmission in the system. So now, because by definition, because lambda is not inside our set D prime, we're going to get one coordinate, at least for which lambda times pi star is greater than psi I star of Z. And so this is by definition because lambda is outside of our reference set D prime. And so now what we're going to do is we're going to define a new queuing system Y, and it's going to be the same as the original queuing system at one exception. So arrivals in Qi happens with rate lambda pi, so this is the same. Departures in Qi different than I star happens with rate psi I of Y. This is the same as earlier. And now we're just going to decouple one queues, and this is going to be Qi star, and they're going to happen with rate psi I stars. And so by doing so, we're just going to take one queue, pull it out of the system, we're going to remove all the dependencies of the state, and this is going to help us. And the way it's going to help us is by construction, the original queuing system X is going to dominate the queuing system Y. And to see why, here, the departure rate psi I of Qi star, it's going to be a maximizer of this departure rate. And because it's a maximizer of the departure rate, we know that the departure rate in Qi star is going to be higher in system Y than in system X. And then we can apply this theorem about stochastic domination, and especially condition C. And now we know that the original dynamics, the system X, is going to dominate this new queuing system. And now actually everything is proven, because if you look closely at this thing, here it does not depend on the state at no moment. And so this is just going to be an NM1 queue. And by choice, by definition, we know that we get an NM1 queue for which the arrival rate is higher than the departure rate. So it is unstable. And because it is unstable, its population is going to diverge towards infinity. And using the domination process, the domination property, we know that the population of the original dynamics are going to diverge to infinity almost surely. And so this is just the trick that we get a queuing system with state-dependent departure rates, and using a right domination hypothesis and using a good auxiliary queuing system, and decoupling one of the queues, we are able to prove instability and actually to get a reciprocal for the results that was proven earlier. And so this is what we prove. This queuing process is stable if and only if lambda I is inside the set D, or equivalently if lambda is lower than lambda star. And so this is interesting because it allowed us to study a system where the fluid dynamics are not defined near zero, which was our main problem for which we could not use the free theorems. And actually, this gives a necessary and sufficient condition for stability under the assumptions 1 to 4 that we had earlier. Yes.
I have a question here.
Yeah.
You have for the stability, you are the strictly inferior of strictly inferior sign.
Yeah.
Here it is the opposite. If you have some equality, what does happen?
So this is one of the questions that is still up in the air. So what we know is that it's not going to be stable if lambda is equal to lambda star, in the sense that the change is not going to be positive recurrent. So which is the main thing. So it's not going to be positive recurrent. Now there is some literature paper, I think, from Sergei Foss and Barakim, for which they are able to study some kind of queuing systems with fluid limits in the case lambda is equal to lambda star, but this is not the usual case.
The way you write it in your theorem.
Yes.
If and only if.
Yeah, sorry. So sorry, I did not mention it, but I say stable for a Markov chain if it is positive recurrence. So it does not englobe null recurrence or transience, but positive recurrence, we know that even if lambda is equal to lambda star. So my guess, but I've not given much thought in it because I didn't have the time. But here, because we are dominating, the system is dominating an MM1Q. Even if lambda is equal to lambda star, this Q is not going stable. So the MM1Q, if lambda is equal to nu, it's so the population still goes to infinity. And so no, it's not recurrent. It's not recurrent, yeah. So it slowly goes to. Yeah, it slowly goes to infinity. Yeah. Limit zero. Yes, but yeah, in any case, it's not going to be. So my guess is we may have no recurrence, but I have not proved it. I have not proven it. But yeah, we know for sure that the system is positive recurrent if and only if we are inside this set. And actually, this can be extended to not only our initial example, but to all queuing systems that match this hypothesis that we had earlier. So if we take a queuing process X such that the arrivals in Qi happen with rate lambda I, departures in Qi at time slot k happened with the given rate psi I, for which the free limit x bar makes the assumptions 1 and 2. So we need also the sequence of fluid scale departure rate to be increasing and to have a limit, so to be increasing and upper bounded. And we also want this fluid scale departure rate to meet assumptions 3 and 4. Then we know that the system is stable if lambda I is inside the set D, and unstable if it is outside the set D, or equivalently stable if lambda is lower than lambda star, and unstable if lambda is.
You exclude the case of equality.
Yes.
Again, it's a disturbance.
Yes, but usually the critical case in queuing systems is not easy to study. So this is also.
Why do you write if and only if or something?
Yes, so maybe. Yeah.
Then there is the equality.
Yeah, maybe. So
something I do not understand everything.
No, but you're right. Maybe I was too quick. So we know that we have positive recurrence inside set D. We have transience outside set D, but in the boundary case, this is, for example, for now, an indeterminate form. Because
here you have lambda, all the lambda I belongs to D, or do not belongs to D, so it's really exclusive.
Oh yes,
the second part, it's not exclusive.
Yeah, no, okay, yeah, I see what you mean.
This is what is there.
Yeah, I see what you mean. You're totally right. There's missing lambda minus its boundary. So sorry, D minus its boundary. This should be the correct form. So but thanks for pointing this out. So yes, we should exclude the boundary because D is not an open set, but yeah. But yes, so this is a necessary sufficient condition for stability. So this we have on one hand stability, on the other hand instability, and the boundary for which it's the twilight zone. No, but you're completely right actually to ask these kind of questions, and it also makes me realize.
The vector can never be.
I know for physics that it is not possible. Don't worry about that.
And so now I'm just going to put, so this is also just a neat thing that we managed to get. So we're just going to change one of the assumptions of the system. So before we just wanted the function psi I to be non-increasing in xj. So now we're just going to add another condition. So we want it to be non-increasing in xj, but increasing in xi. And so the motivation is what we saw earlier is usually in communication queuing networks, the departure rate is also proportional to the queue size. So this is a case that we encounter quite often. And we're just going to see what happens if we introduce these new assumptions. So now we get this new theorem. So if we replace assumption 3 with assumption 3 prime, then we get a characterization for the value of z and the value of lambda star as a consequence. And so now the value of z, so which is the maximizer of the smallest coordinate of the vector 1 over p times psi. Actually, this is just the solution of a system. And so this is a system that you can actually pretty easily solve. And as a consequence, the common value of all the system is going to be the value of lambda star that we are looking for the stability condition. And so to prove this, actually, just a maximality argument. So just going to assume without loss of generality that we can sort the vector by increasing values. So the vector value is 1 over pi times psi I of z. And z is a maximizer of the smallest coordinate of this vector. So we know that the value of 1 over p0 times psi 0 is maximal. And we also know that 1 over p0 times psi 0 is lower than 1 over p1 times psi 1. We know that from assumption 3 and 3 prime, because they are included in one another, psi 0 is increasing in z0 and non-increasing in zi for I different than 0, in particular in z1. And to do so, because this value is maximal, we want to put z0 as high as possible and z1 as low as possible. But because psi 1 is increasing in z1, if we put the bar too low, then the value of 1 over p1 times psi 1 is going to drop below the value of 1 p0 psi 0. And then it would contradict the fact that this is the smallest coordinate of the vector. And so now the only possible case is to have the equality 1 over p0 times psi 0 is equal to 1 over p1 times psi 1. And then we can iterate this maximality argument. It's just a maximality argument. It works well if you're trying to picture it in your head, but yeah, it's just a maximality argument. And then it gives us pretty easily a system of equations for which you can solve. And then the common value for this the system of equations is going to be the critical arrival rate. And so now we can just put it as an example. So going back to the queuing system with n nodes in a circle, the neighborhood for all I is going to be I minus 1, I plus 1. So we're just going to add the conventions with I minus 1 is equal to n if I is equal to 0, and I plus 1 is equal to 0 if we are in n. And so now if we want to obtain the vector z, we're just going to solve for all I and j this system of equations. So zi over zi minus 1, zi plus 1, zi is equal to the same in j. After some calculation, it's so you can do it pretty easily by hand. We're going to find that all the values of the vector z are going to be common. So zi is equal to zj is equal to a given value z is strictly positive. And as a consequence, the critical arrival rate that we had is just z over 3z, 1/3, so which is the stability condition that we had earlier. So now we can change it a bit. So if we are considering n nodes in a line, so we're just going to change two neighborhoods. So the neighborhood of node 0 is just going to be 0 and 1. Neighborhood of node n is n minus 1 and n. And if we solve the system, so I'm not going to show it here, but you find that lambda star is equal to 3 minus the square root 5 divided by 2. And so this is interesting in two ways. So this is higher than what you had in a circle. So this is something that has already been displayed. If you are in a node, in a line topology, the two n nodes actually have a higher throughput than the inside nodes of the line. And so this allows the stability condition to be larger. And the second thing is it's still under the theoretical upper bound of lambda is equal to 2/5, which is obtained with decentralized CSMA. And so if you want to read more about it, there's a quite beautiful paper by Sebastien Alexander Stoliar that is displaying so with a lot of combinatorics and fluid limits. So if you are interested in, should definitely check it. So now just to conclude this, the third example, and so this was my motivation to
come back to the
yes,
last result. This means that this value do not depend on n.
No. So you can get an infinite line of yes. But,
I would have believed.
Yeah, but
on a circle, I understand. But,
no, sorry, maybe not the infinite line.
Infinite line, no, because I mean,
the
fluid methodology.
Yes, sorry.
So the Lyapunov function.
No, but that's infinite.
Any finite.
And in fact, infinite, but not as a corollary.
Yes, not as a corollary. It's always a problem when you want to jump from finite to infinite. But so the third example, so this was my motivation to study this problem. So I'm going to show that this can be applied to a much more complex fluid network. So we're going to define something we call the multi-class interference scoring network. So we take n locations in the squatters grid. At each location, we are going to place 2 to the k minus 1 q with k an integer greater than 2. And each of these q's are going to be indexed by a subset C of the set 1 to k. So just to understand the physics of it, this subset C is going to be a set of bands, and the user are going to interact using wireless communications. So we're going to assume that the arrivals in QIC are going to happen with the rate lambda 1/n, because all of the Q's are the same when it comes to the arrival process, times PC with a given distribution of probability P. And the departure in QIC are going to happen with the rate that is a Shannon rate. So we get 1/LC. So LC is going to be a quantity of information that each user is going to receive when arriving in the network. And then here we're going to get the signal, the number of bands on which the user is transmitting, divided by an interference parameter, which is going to be the signal attenuation from the Q that we are looking at to all the other Qs in the system, which is represented by this path loss function Ln, times the number of other messages in the system, so which is going to be the Q sizes of the other Q sizes in the system. And because we are in a multi-class setup, we're just going to interact on the users that have a non-null intersection with the set of bands that we are looking at. And so this is just a linearized version, sorry, of the Shannon rate, which is log of 1 plus the signal divided by noise, which is with the thermal noise density that is n, plus the interference power in the system. So this is actually a bit a more complex queuing setup, but it matches all the assumptions that we had. So we can prove that the fluid scale departure rate actually converges to a given function. We can easily see that it is zero homogeneous, that the fluid model matches the assumptions 1 and 2. It is increasing in Q size, decreasing for all the others. Sorry, there's a typo here, it's XKU. So it increases in the Q size, it decreases on the other Q size. We get a fluid model that matches all the assumptions. So we get assumptions 1 to 4 and assumption 3 star. And so we can solve this system. So now I'm not going to display everything, but using the squatters property that we had and simplifications and combinatorics, we can remove the dependency on the Q locations, because we're on the square torus, so invariant translation, and so everything works quite well. And so in the end, we get a rather simple system that we can solve. And for example, if we assume something which we call a symmetric system, so all the users having the same band configuration, so whenever the set C and D have the same cardinality, we get PC is equal to PD and LC is equal to FD. So we get an immediate solution for the system, which through combinatorics can be reduced to the main results that we obtained in a paper with François that is posted in arXiv. And so this shows that and so we get as well the same differentiation. So stable if we are under this value, unstable if we are strictly over this value, and the twilight zone between if lambda is equal to lambda star. So this is not a case that we investigated yet. Yes.
Maybe interesting for you to say a few words on the boundary part,
Yeah.
5G boundary part interpretation of the dynamics, the earlier one.
Sorry, which one? This?
Yeah, right. The boundary part.
Yeah. So like François suggested. So here, so this is so the goal here was to find a stability condition for actually this is not the primary system that we wanted to study. The primary system that we wanted to study is actually a spatial queuing network for which the locations of the queue are not fixed points in space. They can be actually they can spawn the users arrive through a Poisson range, so they can arrive at any location in a continuous space. And so by the use of the stochastic domination, we can bound this spatial queuing system from above and from below by two of these interference queuing networks. And actually what's interesting is because we get at the beginning a fixed finite region of space, so we're going to mesh it with cells of size epsilon. And at the center of each of these cells, we assume that all the users are going to be located at the center of each cell. And so we're going to find an appropriate path loss function L to be able to dominate the dynamics from above and from below. And so what's interesting in this thing is as the number n goes to infinity, or as the mesh, the grid parameter goes to 0, actually, this converges to the same value for the critical arrival rate. And so this actually methodology allowed us to obtain a stability condition for a continuous spatial queuing network. So like I said, it can be applied to more complex. And so this is not the most complex. I didn't want just to go through all the details of what we had. And so actually the motivation for this spatial queuing network was a 5G wireless network, because with 5G, you start to get bandwidth partitioning systems. And so this is the rationale behind using this subset, this set of bands. Because in a 5G network, you're going to be allowed to be allocated a certain number of resource blocks, which corresponds to a certain frequency. And you're not going to interfere with the same power with all the users in the network. And so this is one of the main novelty of 5G networks, because this service differentiation allows to get a much broader bandwidth for users and to increase network performance. And so our goal here was to see how this bandwidth partitioning could change the stability condition for the system. And so we can even get an interesting interpretation for this stability condition, because it may seem complicated on the at first glance, but here is 1 over, so this is the mean value, so this is an integral of the path loss function. It corresponds to a global interference term in the system. This sum corresponds to the load that is going to, so the average load that is induced by one user in the system. And because we are going to get k parallel channels for users to transmit, we're just going to multiply this capacity by k. And so this is what gives this stability condition. And the last thing, so I'm just going through this, but this system actually does not only hold when you are taking the symmetry assumption that allows to simplify everything in terms of combinatorics. It works also when you remove it. And so we get another heuristic that is very performant when it comes to getting the critical arrival rate in the spatial queuing system. And actually the stability condition that we get is actually tight. And this is very interesting in itself, because it allows, like I said, to obtain stability and instability just by solving this simple, in our quotes, system of equations. So yeah, like I said in the conclusion, so this we managed to obtain a simple condition for stability and instability for queuing networks when the fluid limits is matching certain conditions. By introducing just a slightly different assumptions, we obtain an explicit way to compute the critical arrival rate lambda star. And like we saw, we managed to compare the stability condition for different queuing system with it. And so, like you said, this was the last open question, but what happens when lambda is equal to lambda star? And so this is, like I said, not investigated. In some cases, you are able to obtain results for the Markov chain when lambda is equal to lambda star using field limits. But in a general case, it can be pretty hard. So we have not investigated it. So if you have any ideas, feel free to propose them. But right now, it's still an open question. So thank you for your attention. If you have any questions, feel free. So I'm just going to mention some references before. So we get the 2 original papers that motivated the work. If you're not familiar, that's Jim Dive's paper on fluid limits that actually does not have only one result, but 5 or 6 different, and it's quite well written. If you want to see why unstable fluid models can work, unstable fluid models can have stable queuing networks, Bromson's paper is quite interesting in this regard. And then if you want to read more about the special queuing system, we have a paper with François with it on archive, or if you're able at the end of June for my PhD defense. So thank you.